Hello everyone and welcome to the CSE116 Task 4 overview. Now in this overview video we're going to be going over how to set up kinda BFS in the game engine. So we know by now you guys are probably pretty used to BFS with the problem set. You guys have got a lot of practice with that by now. So we're just going to take a look at it in the game engine and kind of see what we got to do there. That's the bulk of what we're going to be talking about in this video, because most of the other things we've either already talked about or you guys have done them in like a previous task, and it's just more reinforcing kind of that workflow. So we're going to start there, talk about BFS some more and how to actually do this in the game engine. And we'll also be talking about how to test that a bit to make that a bit easier. So we could just jump right into the doc. Pranked ya. Actually, we're looking at the game. So yeah, here is the roguelike, and this is the roguelike completed with the CU, which lets you procedurally generate levels. Whoa, that's awesome, right? Yeah, it's super cool. So don't you guys want to learn about procedural generation? Do the CU. So anyways, yeah, this is the roguelike. So with the CU complete, it's procedural generation. You know, I'm playing the game, I get to find stuff in a roguelike. But I'm going to try to find an example here. Yeah, so right here, this is perfect. This is pathfinding. So find path, avoid walls. This enemy is chasing me, avoiding all the walls and actually getting to me like smartly. So I'm going to, go over here, let him recalculate his path again once he gets to where I was. And yeah, as you can see, he's avoiding the walls, he's making his way to me. This is working great. So this is what your implementation will look like when it's actually done. I'll play through this roguelike for another like second or two. These like random levels here, it's like this one's based on like the Binding of Isaac. So and if you die, by the way, you'll get a whole new random set of levels. Like, it's really cool. You guys could even like make your own levels and add them here. It's really cool. And like, this is also, if you can't tell, mixed with the behavior of the decision trees that we're giving. So yeah, it's like a real game. You can actually play the game. That's a very loud sound effect, but yeah, so it's cool. I recommend to like, just play around with it, and this one, yeah, so this one heals with the decisions until it's full health once it takes damage. It's just fun to play around with, so. Okay, so yeah, the first thing here, always, read all this stuff. And we are going to want to make sure we download testtask4.java and put that in the game engine so we can start working on that stuff and download these testing files, and of course anything else here. We're going to be reading it. And yeah, again, this says we're going to be dealing with BFS, and that's really what we're going to be talking about in this video. So yeah, by the way, if you guys did not do the follow path CU in task 2, this is going to look a lot worse in the game engine, like when you're actually playing the game, because your enemies and agents are going to calculate their path, but they're not going to be able to follow it. Aww. So yeah, anyways, let's take a look at the specifications here. So this is the bulk of the task. The hardest part of the task is going to be making the find path avoid walls method inside of pathfinding. So you guys have to, or pathfinding utils. So it's a static method, and it takes a level, vector2ds as a parameter, returns a linked list node of vector2ds. Now, I think the number one thing that you guys should be considering before starting this method is to just visualize how it should actually work before typing any code. So looking at images like this example here are really useful because they help you understand what's even going on. So number one thing that we have to first realize is that we're looking at a level, right? Like this pathfinding, everything about our pathfinding has to do with the level and how we could actually calculate the path and where we're not allowed to go in this level. So in the perspective of this enemy here, there's walls all around it, so it has to go down and around. It can't go through the wall. That's the whole point of the method. So right off the bat, we have to think, how could we get this level data and translate this into some useful pathfinding data that will allow us to actually calculate a path using BFS that we learned in class. So there's a few ways we could actually do this, but it all comes down to reading what's in the level and making some assumptions from there and calculating the path. So we can analyze this data in a few different ways. One of these ways, like we learned in class, is to build this data into a graph that we can then operate on and do our search on that. And that's probably the one that is the most, like, that's the approach that we'd probably all expect you guys to take. So you guys could actually make your own graph class in, well, you could put it technically wherever you want, but I would put it in the data structures package here, in app, game engine, model, data structures. If you want to make a graph, you could do that. Also, you know, just saying, there is that graph from the problem set that if you guys want to use, you can, of course. Like, you know, it's not cheating or anything. If you use this graph, go for it. You could totally do that. You could just, you know, in the method itself, you can make your own hash map adjacency list. However you want to store the graph data, do that however you want. So if you did want to just copy that in, like copy this code, and by the way, this is just the GitHub repo for the problem set. But yeah, you could just copy this code and go over to the, you know, data structures, make your class, and paste it in. Totally able to do that. But yeah, that's up to you. Now, another approach to this problem is to not actually build a graph. I'll explain why that's actually possible here. So if we look at a vector 2D position, we will be able to see that from that position there are 4 neighbors, right? Up, left, down, and right. Now, the position at that location is either a valid position to traverse or it's not valid. And what I mean by valid is if the game object at this location is solid, it's not valid. We can't go there. So we would not consider this point. Also, if, say, this wall here wasn't a wall, but it was actually out of bounds, then it wouldn't be valid. So, like, if we were in the top left here, I mean, obviously there's walls covering this entire boundary, but let's imagine there wasn't a wall in the very top left point here. The direction to the left of me, this point would not be valid because it's out of bounds of the level. So with that information, you could actually traverse BFS, and when you're looking for your next neighbor, you could calculate that because we're dealing with vector 2Ds. You know, this is a unique scenario in a graph problem where we're actually able to calculate our neighbors instead of having a preset graph, an adjacency list. You know, because we could totally build a graph. And if we were to build a graph, it would basically be the same exact thing that I just said, but the neighbors would have already been calculated for us. So let's take this example here where this enemy is on that picture. So the enemy is in this node, and it has 4 neighbors, okay? And I'll draw them like this. And so if this was a graph, like a pre-built graph, this would be a key in our adjacency list, right? So this is like a vector, it's 1, 1, okay? So this vector right here, 1, 1, has all these 4 vectors mapped to it in its adjacency list, right? Okay, it's like a donut, okay? So all of these here, these vectors are in its adjacency list. Unless, when you build the adjacency list, you do not include the objects that are solid. So if that were the case, then we would not include this one, or this one, or this one. So at the position 1, 1, there would only be 1 vector in our adjacency list, which would be, let's see, it's, oh man, it's 1, 2. Yeah, okay. So this would be the only key or value mapped to this key here, 1, 1, because that's the only valid spot that we could go. So that's how it would work if we built a graph. We would notice like, okay, there's only one direction, so we would go in that direction, right? Um, However, there's another scenario. So let's take this point here, right? We're in the very middle. And this node's scenario, this is not solid, this is not solid. This is how the data is represented, right? This is our key mapping these two values, right? So this is just like some visualizations here of these nodes of how we extract the data from the level. But that's part of the problem, right? We have to extract the data from the level. Conveniently, though, we are passed in a level in the find path avoid walls method. And with that level, we could call methods such as get static objects or get dynamic objects, as shown right here. And like I said, we do not want to consider objects that are solid. So one strategy here is using either the graph that, you can either make your own graph class, you could just use an adjacency list, or you can copy the one from the problem set or the slides. However you want to do it, if you want to use the graph approach, something that might be a smart idea to do would be to, go through the positions and map every vector 2D position to its neighbors in the adjacency list. And in doing that, maybe you would not include the ones that aren't valid, which is the out of bounds or the ones that are solid. Those are not valid. So that's the way to do it. If you were exploring, in BFS and you're about to look for new neighbors, you could calculate them using the other approach in the algorithm itself. So if we were at the position 1, 1, well, here, I'll draw this a different color. So if we were at position 1, 1, we know we could physically calculate the positions of our neighbors, right? So it would be 2, 1, 0, 1, 1, 0, and 2, 1. Or sorry, 1, 2. And then we could check if each of these neighbors are valid, and if they are, then we could add them to our BFS queue or whatever. So I would just consider some ways of completing this problem. If you guys want to use the graph that we give you in the problem set, feel free. And if it makes more sense to you to do it in the approach where you just calculate your neighbors manually and then assess if they're valid, you could also do that. So there are a few ways to do this problem. As long as you get the right path, then that's what matters, right? We're not physically checking if you make a graph class or any of that. We're just checking that you return to us the right linked list nodes of vector 2Ds. So a big part of this, though, as well, is testing, right? So all of this stuff is decision stuff. You guys should all be completely familiar with this. It's just the polymorphism stuff we talked before and the level parser stuff. However, testing is another challenge here. So the first step is to write a testing utility. This utility, I'm gonna be blatant right now and recommend it. I think you guys should try to do this with recursion. It'll make it a lot easier and cleaner. You can do it however you want, but I think this will be a lot easier with recursion. And make sure you're actually using this testing utility in all of the tests you write for find path avoid walls. Because it's just once you have the testing utility written, why not use it? It's just going to help you pass quicker. But yeah, so find path avoid walls testing. This could get a little messy because you have to create your own levels, right? Now, that's very annoying to do manually, but it is totally doable. So a way better way to do it is to use the given level editor that Jack made for us here. So the level editor is nice, I get to scroll out and all that. But we could totally make levels to test our pathfinding. So one that, I would do a pretty complex one. Once you guys are further down your implementation and want to get make sure you're doing it right, I would do one basically that looked, I don't know, something like this. something just like real messy, right? Like that. And then I would have like the start here and end here. And so I literally just made this level in like what, a few seconds, right? And I know this point on the grid is one, or sorry, it's one, 2, 3, 4, 5, 6. So this is 1, 6. So this is where I would start in BFS, and I would want to end at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. So 10, 6 is where I'd want to end, right? So what I would do is, I'd make this level, and, I would name it like test level, then maybe export it. And now we have the CSV file. With the CSV, we could go directly into the game engine here, and I have to open this up. But I'll just put it here for now. Don't add it to Git. So put it in the levels directory of your data file here, which is above the source. So I would go like levels, and I'd probably put it in the testing folder, drag that in there. And now I got my test level. This entire CSV file is what I just drew, right? It's everything there. So it's just the assortment of walls, which is really what we want. So super handy. Play around with the level editor. You can make these a lot bigger too with the width and height. You could go way bigger than this, or shorter if you want like more simple tests. But I definitely recommend using this. It's gonna, like, if you guys trust me and just use this, it's gonna save you a lot of time instead of manually writing your own levels. Like, who wants to do that? But then when you actually want to get these levels with the level parser, it's very simple. So I'll just go into some random file, random test file. I know you guys are supposed to copy this from the handout, but I'm just gonna write this just so I could show this example. Okay, finds path, avoid walls. So I'm gonna show you guys how to actually get this data from the level editor. Very simple here. So the level parser makes this really easy because we get to use a static method that it provides. We could just call the level parser class, right? So level parser dot parse level, and we have to pass in a game and a path. So as for the game, you could really make whatever game you want. I'll probably just do sample game. Well, not any game you want, but I would do like a top-down game just to be safe. But I would do like a sample game, and I'll just call it game equals new sample game. Just simple, and then pass that in. And then I have to give it the name of the directory of the level I just made. So here, we start in the levels directory. So I wouldn't type like, data/levels. I would start in the levels, and I'd go testing/test. I named this really confusing, .csv. Okay. And so this returns to us a level. So what I'll do is I'll store that in a level, and I'll just call it level, and boom. Now I have the level. And, what I could do here is, level dot, I'm just going to do this so I can show you guys with the debugger. Get dynamic objects, right? I'll put a breakpoint here, and I will debug this method. Oh, okay. So I'm getting issues here, actually, because I did not realize I don't have a player start location in the level, which is a problem. One note is when you're making these editors, or when you're making these levels in the editor, make sure to include a player start location, or else it's going to break. So I'll just add like the player here. The player start location is necessary. So I'll put the player there, export the level, do the same exact thing, put it back in, boom, okay. Okay, yeah, so when I run the debugger now it works. And if I go access the debugger here, and I go into the level that we just made with the level parser in the file that we just created, we get to see that it has all the static game objects that we expect. It has 61 walls. There's a wall everywhere that we expect it to. I'll pick a random one just to confirm. All right, so this wall is at 1.7. Let's make sure that there's a wall at 1.7. All right, 1, 1, 2, 3, 4, 5, 6, 7. Yep, it's this one right here that I just deleted. So awesome. This is a very useful tool for testing. Definitely use it. And once you have the level itself, Now it's very easy to just call that pathfinding method because it takes a level, and let's look at it over here. Yeah, so find path of void walls takes a level and 2 vector 2Ds. So what you could do is pass it that level that you just made, and then find 2 points that like you want to run the BFS on. So I would pick the starting location as like this point right here. So I think we said that was 1.6, and then the second location over here, which is I think that was 10.6. So if this works, then that method, that find path of void walls method, should return to us a linked list node containing vector 2Ds starting here at this very point, going all the way through until we got here, right? And all of these vectors, all these, like, I place these just for visual. All these potion vectors here should be in that list that's returned to us. And that's like, you should write tests before you actually implement the find path of void walls method, because then it would save you a lot of auto lab time, that's for sure. Because once you pass the testing phase, then your implementation, you could just keep running your own test. And once you pass your test, you know that you're probably got a working implementation. So I would definitely make levels like this and, explore some complex ones, like if one of these works, try to think of some edge cases, right? Like what if it was blocked off here and I still had these start and end locations, right? I should return null in that case from the find path of void walls method, because if no path could be found, we should get null. So try to think of some edge cases, make some like wacky levels, have fun with it, honestly, because it is kind of fun making the levels in here. And just make sure that it works according to how it should. So definitely take a look at the level editor. I guarantee you it'll save you time. Regardless of how you implement your BFS, the testing should remain relatively the same. You're still going to be expecting the same input and output. I give you a game and a level and 2 vectors. I expect the correct path to be returned to me no matter how you implemented it. So that's why testing is recommended first. But yeah, that's basically the testing part of it. And just a little bit more clarification, I guess, because I do want to talk about the validate path testing utility one more time here. Validate path is fairly simple in the sense that we're just making some local assumptions about the vector 2Ds that were passed in to validate path. So we're returned a linked list node. We are passed in a path, right? And we are supposed to validate it. And a path is just a linked list node of vector 2Ds. A path is valid if every vector 2D in that list is a whole number, meaning that there's no decimals, and if every 2 vector 2Ds that are adjacent to each other in that path only differ by at most 1 tile apart. Not at most, at exactly 1 tile apart. That means that the difference of any 2 adjacent vectors in that list must be 1. Okay? So that's what the testing utility is. And I recommend recursion for that. So definitely give that a try. This is the last LO task, so spend a lot of time on this. I would recommend doing testing first. That would make your actual implementation go a lot quicker, because you could just spam your tests as much as you want. For Autolab, you have to wait and all that. Like that's egregious, right? You could just write your own tests first, get those passing in Autolab, and then when you're actually writing your implementation, you could just spam your own tests over and over. And once those pass, you probably got a working implementation. So I recommend that. And yeah, I think that's pretty much all I have to say about this task. It's less material I have to cover here because it's really just this one method and the testing for it. So definitely utilize the help that you could get at this far in the semester. You guys made it this far, so I believe in you to all complete this very well. But post on Piazza if you have questions. Office hours, and yeah, that's pretty much it. Good luck on the task.